Hi, and welcome back to Troubleshooting Python Application Development. This course is designed to help you speed up your Python applications and reduce its memory footprint. One of the core tasks of any Python application, or any application really, is to interface with the external world and get data, post data, and perform other actions. When we do this, it's often called an I/O call. Input output, and because we're leveraging external resources, we often have very low control over how long these I/O calls would take. In the last 3 sections we talked about profiling, which is we looked at how we can measure the time and memory consumption of our programs. We then looked at Pythonic patterns that can help us speed up our programs, and also looked at NumPy and numexpr, which are 2 libraries that can help us speed up in-memory calculations. So now in this section we're going to talk about what happens when we first get the data into the application or get some data out of the application. How can we speed up our I/O heavy tasks with concurrent programming? So what is concurrent programming? Concurrent programming is when you switch to a different task when one of the tasks is waiting for the I/O function to complete. Imagine if you have a program that reads a file. When the Python program is reading the file, you're waiting for the operating system to assemble the file, assign the file to you, and return the content of the file to the Python program. This may take half a second, normally negligible if you are running a very small program, but if you're running a data pipeline or any other application that performs a lot of I/O calls, the 1 second can stack up. Concurrency's idea is very simple. We start a call with the operating system, and we let the operating system do things in the background. Meanwhile, we do something else, like start another I/O call. So when the first I/O call returns, the second I/O call is already underway, and in aggregate, running many I/O calls will be cheaper in terms of time. To illustrate the issue about I/O calls, I'm going to use an I/O call that has a lot more latency, i.e. scraping websites. So scraping websites take a long time because we need to establish an internet connection, retrieve the website, take the data back in, and analyze the data. So this usually takes a lot more time and is a lot easier for us to illustrate the concepts of concurrency than something like reading a file. Most computers nowadays have SSD, solid state drives, which have very, very fast I/O speeds. So to demonstrate the idea of concurrency on SSDs, it would take us a lot more complex problems. Web scraping is a very simple problem that demonstrates the issue of I/O calls, especially when we have serially executing web scraping calls. That takes a long time. So in this section, we're going to do this in 4 steps. Number 1, I'm going to show you the problem of serially executing web scraping calls by taking a few URLs from a popular news website and just using requests, the library, to get the web page and see what the status code comes back as. If the status code comes back as 200, it means that we've successfully scraped the website and all is well. We also time how long it takes us to scrape about 10 websites, and we use this as a baseline to compare our 3 solutions that are coming up in this section, i.e. simple asynchronous programming with coroutines and G-events. We then look at the second solution, which is event-driven concurrency with Tornado. And then in the last video we look at concurrency and futures with async I/O. So G-event and Tornado are both third-party packages in Python, while async I/O is native to Python if you have Python version 3.4 or above. I don't see why you shouldn't, but obviously sometimes if you work in a corporate environment or organization is slightly less quick in adopting new Python versions, you might not be able to use async I/O. That being said, as of today, we're on, I think, 3.6.5 is the stable release. So it should be very likely that you can use async IO, and the benefit of that is async IO is built into Python. You don't need to download any new libraries, and also is very fast. So let's dive in. So what's the problem of serially executing web scraping calls? We're going to demonstrate this problem in 2 steps. So we're going to look at using requests to scrape the HTML of a web URL, and how we can time 10 web scraping requests and illustrate how long it is to actually serially scrape these things. Let's go in and take a look. So I'm in my PyCharm, and we are in the accompanying code file serialscraper.py. We first import requests, which is a very popular library in Python, very well written library, very simple API to request connections with remote servers. That sounds very abstract, but one of those applications is to request from a web server a website and parse it in Python. And that's what you know as scraping. So we need requests to scrape and connect to websites, and we need import time to measure how long it took us to scrape all these websites. We then create an empty array, an empty list, results, and we have a list of URLs, which is basically recent articles from BBC. So we have 11 URLs. To time this is very simple. We simply use start equals time.time. We run our code, and then we look at time.time again, which is Python's way of calling now, minus the start time to see how many seconds has passed. In the middle, all we do is, for every URL in URLs, we request get that URL, and we append the status code of that request into the results list. We then print out the results and print out how long it took us to do everything. So recall that from our first section, this is not the most fine-grained way to time how long things take, but this is good enough for our purposes when we're simply trying to see how much faster we can go if we're doing concurrent execution of web scraping calls. Let's run this and take a look. So I just ran this, very simple. It returns an array of numbers, and each number is 200. 200 is the status code for success in the HTTP protocol. And so what we have here is we have scraped all the websites, and requests has successfully made a connection to each of the URLs and retrieved data. And we can also see that we've done this in 3.55 seconds. So in the next few videos, I'm going to introduce how we can do concurrency in Python, and the aim is to try to beat this number. So bear in mind that because we only have about 10 URLs, the power of concurrency isn't very clear cut. But if we have thousands and thousands of URL calls to do, for example, if you're trying to resolve shortened links on Twitter, then you noticeably see the speed up when you're using concurrent programming versus serial programming. And that's all there is to it. We've just used the requests to scrape the HTML of a web URL, and timed 10 web scraping requests. Took us 3.5 seconds. Let's see in the future videos whether we can beat this baseline.